I wonder if we can talk about what it has been like to have been in the room when the folks at Bell Labs started experimenting with the transistor. That first step that took us from vacuum tubes to integrated circuits. Well, NTT's Phi Lab research scientist Tim McKenna is working with thin film lithium niobate to develop photonic integrated circuits that are part of the broader NTT vision of an all photonics network. Welcome, Tim.
Thank you, and thank you for the introduction. My name is Tim McKenna, and I'm with the Phi Lab at NTT Research in Sunnyvale. So that's the Physics and Informatics Laboratories. And today I'm going to talk about the future of computing. So right now, we're at a time when quantum computing, it's officially gone mainstream. After decades of work in the field, all of the household names are now involved. And so for superconducting circuits, that's probably the most popular form of quantum computing right now, and it's pursued by Amazon Web Services, Google, IBM, Rigetti, and probably many more that I haven't listed. In this form of computation, it has to operate at very low temperatures. So here's a dilution refrigerator that can cool these quantum computing processors, these little chips. It can cool them down to almost absolute zero. But if you notice, for a little tiny chip, you actually need to put a tremendous amount of energy to cool it and have a tremendously large apparatus to make those processors work. And on the right, this is me with my good friend and lab mate, Jeremy Whitmer, and we're wiring up some of the first transmon qubits that were made at Stanford University about 5 years ago. But there are other ways to do computing. There's also some photonic circuits that are being pursued by Intel, Xanadu, and PsiQuantum. You can also do quantum computing with trapped atoms and ions. This is pursued by IonQ, Honeywell, Cold Quanta, and others. But all of these schemes, there's still many problems to be solved to make these truly viable solutions. Yes, theoretically the performance could be amazing, but there's still real-world engineering and actually just fundamental physics problems to be solved, including scalability, qubit lifetime. So quantum information, it's extremely delicate. So even a little bit of noise or a little perturbation from the environment can destroy the entire calculation. There's also a really big need for error correction. That's an outstanding problem, and it's its own subfield onto itself. And algorithm development. So you can't program a quantum computer like you can program a traditional computer. And the algorithm development, they actually haven't quite caught up to the hardware itself. So these are really big problems. And I guess my main point here is not that quantum computing will work or it won't, or one company is going to be successful and another's not. My main point here is that the world, there's a tremendous appetite for new modalities of computation. We've kind of hit the end of the road with traditional computing based on silicon electronics. So the problems that we're trying to solve today, they're much bigger than the computers we have today. So I think actually what this shows is I think some combination of optimism and desperation have led us to kind of just pursue all options here. But NTT Research actually has other ideas. So we have other methods of computing that kind of go against the grain of traditional quantum computing. And these are based on integrated nonlinear optical circuits. So that's what I'll talk about today, and I'm really excited to share. So why even look at optical computing? It's not really a new idea, but when you look at what happens to a CPU, when they go faster, they melt. And right now, what I mean by that is they just get too hot. You can't really break about a 5 gigahertz clock rate. You can see we've basically been plateaued for a decade with clock speeds. So here we are, the world's problems are getting bigger, but our computers actually aren't getting bigger, and we need to solve that. And what's really exciting about nonlinear optics is when you do computation with pulses of light instead of electrons, the faster your clock rates, the more efficient the computers get. And this is incredible. This is basically the opposite of electronics. And how this works is, oh, and by the way, you can go up to terahertz clock rates. So you can go up to clock rates that are 1,000 times what you can do with traditional silicon electronics. So there's clearly, a lot of reason for us to pursue this. But I'll just explain a little bit why the efficiency can go up. So basically, if you're doing computation with optical pulses, if you can make the pulses shorter, you can fit more pulses into the same amount of time. So you can do, if each pulse kind of represents a clock cycle, you can do, in this case, with the high data rate stream, you can do twice as many computations for the same average optical power. So it's actually that simple. If you can make your pulses shorter, your computers get more efficient. And so if that's true, why hasn't it happened yet? And that's really the topic of this talk. This looks great, and I'm going to tell you about how there's new technologies and new discoveries that actually can make this possible. So far, optical computing, it's not been able to compete with silicon electronics. So there's three main things you need to do good computation. You generally need nonlinear processing, memory, and gain. In electronics, the transistor basically saves the day on all counts. It's a tremendous device, and it provides nonlinear processing with switches. We have DRAM and memory, and we have a lot of gain at our disposal. So basically, it checks all the boxes and then some. Traditional photonics, it hasn't been able to meet these requirements. We didn't have access to enough nonlinearity, memory, or gain, but that's different now. So there's a new platform based on thin film lithium niobate. Basically, these are integrated circuits made out of not silicon, but they're made out of a different material called lithium niobate. And we at NTT Research, we've made devices that check all of the boxes. So we've made basically the first building blocks to do optical computation in a real way, not in a theoretical way, but in a real way that can change the world. For nonlinear processing, we have an OPO. This is an optical parametric oscillator. And don't worry about everything that means, but basically in the architectures that we pursue at NTT Research, it's basically analogous to a transistor, if you want to think of it that way. We also have memory. So what's really nice is we have really low loss waveguides, but we also, in this platform, we have access to quantum limited amplifiers. And what I mean by that is, unlike in electronics, you can amplify a trillion times your signal. And the only added noise is that dictated by just the fundamentals of quantum mechanics. There's no excess noise added, and that's a tremendous advantage. So we've actually built these building blocks in the lab. So we have an OPO with the world's lowest threshold power. Previously, these OPOs, when you tried to integrate them on a chip, they either didn't work or they worked inefficiently with maybe 1,000 times more power than this one. We have low loss waveguides, very high fidelity nanopatterning has enabled this. And we also have the world's highest gain, most efficient amplifier with 71 dB of gain. So we're in this great place where we've showed the building blocks and now we're pursuing full architectures. But I want to take a moment just to describe lithium niobate in a little bit more detail because we may not have all heard of it. So it's a man-made crystal, first synthesized at Bell Labs in 1965. And it has amazing physical properties not found in silicon. So I think most of us are probably familiar with silicon photonics. This is like silicon photonics. However, it has many properties that just aren't found, that you can't actually realize in a simple way in the silicon photonics platform. The first of which is the electro-optic effect. So this is inherent to lithium niobate, and it's actually why lithium niobate, not in integrated circuit form, but lithium niobate, the material, has been used in the telecommunications industry for, a long time, so really since around, the 1990s. So for the electro-optic effect, basically, if you apply a voltage across lithium niobate, it will modulate the speed of light of a laser beam traveling through the material. And that's if you hook that into an interferometer, you have a data modulator. It also has the piezoelectric effect. This is a pretty interesting effect, and it's actually useful for RF filtering. It's found in many high-performance RF filtering applications, and these types of devices are actually found in your cell phone also. But really, the second-order nonlinearity, it's the star of the show for us. So this lets us convert one wavelength of light to another wavelength of light, but it also has some really interesting quantum mechanical properties, such as squeezing and other things that make it very versatile for our uses. So you can see we're kind of pursuing things similar to silicon photonics, but it's very much a complementary platform because it can do things that simply cannot be done otherwise. So now I'll draw an analogy to try to explain really what's going on. So when silicon photonics was invented, I guess around the year 2005, it started to get more traction in the academic world. But basically what happened was we basically took an optical fiber, which is used to transmit data signals, but we took that and we shrunk it down onto the surface of a chip. So here we can see at the top is an optical fiber, and then at the bottom is an integrated circuit where you see a very small silicon waveguide. And this changed everything. It was actually a revolution for telecom, for sensing, for linear optical computing, and also for LiDAR. So there's a tremendous advantage to make integrated circuits on this platform. And the same is true for lithium niobate. Lithium niobate, it's not a new material. We've been able to make devices out of it for a while, but those traditional devices have not had the performance needed to do the things that we're discussing today. So we can basically take lithium niobate, and now we have the fidelity to pattern it basically on the same scale as silicon photonics. So you can have circuits that are roughly just as compact and dense, but you have the functionality and the high performance of lithium niobate. So this is really why we expect a further revolution based on lithium niobate, because we've already seen what silicon can do in the photonics world. We've already been there, and now we're going to see what the future holds. So we're really aiming to combine the scalability of silicon photonics with the performance of lithium niobate. And the performance is really high. So on the left, we have this left bar. We have, I guess it's on your right, but we have traditional lithium niobate modulators. And when you operate around 40 gigabaud, dual polarization, QPSK, on a single carrier, you get 160 gigabits per second. That's pretty simple math. But with these thin film lithium niobate modulators, their bandwidths can far exceed 100 gigahertz. They can far exceed 100 gigahertz. This is all because we've miniaturized the modulators. So the phase matching conditions between the traveling wave microwave electrodes and the light that propagates in these interferometric waveguide structures, it can be very well matched. The other thing that's pretty amazing is the V pi of these modulators can be 1 volt or less. I mean, that's tremendous. It's those two things that can really enable ultra low power, ultra high capacity communication. So here's an example in the literature of a 2 terabit per second data stream, all on a single carrier. So it's really special. But also, it doesn't just do electro-optic devices. It also ushers in a new era of nonlinear optics that can do things like computing, like the things we're interested in at NTT Research. So the field of nonlinear optics, it really got its start in the 1960s after the invention of the laser, and lithium niobate was one of the very first materials developed at Bell Labs to do nonlinear optics. And so in bulk crystals, you could shine light through the bulk crystal, and you could basically do all of the nonlinear optical processes we've discussed today. Then in the 1980s, these weakly guided waveguides came out, and that was a huge breakthrough. But now we don't have weakly guided waveguides. By strongly confining the light to the waveguide, we've basically, improved the performance by orders of magnitude again. So not only do we get the scalability of silicon photonics, but we also, by shrinking the waveguides and making them very small, we get enhanced electro-optic effect to make better modulators. And we also get enhanced nonlinearity to do computation and to make really high gain amplifiers. But that's not really all that's happening. If you also confine the light to ultra short pulses, like we discussed, so if you also confine the light to small pulses, you get even greater improvements. Just the way confining the light in the transverse direction in your waveguide increased the performance, well, if you actually take the time domain now and shrink it in the time domain, the same thing happens. So this is tremendously powerful, and now we actually have techniques that really do rival traditional computing. So let's try to figure out what the future is. So that actually, everything I showed is actually happening today. Some of those results might only be 6 months old. It's a very rapidly developing field. But I want to now talk about what we're going to do moving forward. And to do that, I want to take a step back down memory lane and look at the development of the modern silicon CPU. So the first transistor was developed at Bell Laboratories, and it was made in 1947. And the inventors were John Bardeen and Walter Brayton. And actually, I love this magazine cover. You see that the two inventors are actually standing behind their boss. And their boss is the one, it's Bill Shockley. He's the one that's on the bench looking at the devices. And Bill had a personality to him. And you can tell that the two people that did the real work aren't actually that happy in this picture. But everything was okay. They all got Nobel Prizes. And everyone was happy in the end because they ended up changing the world. But it all started with a benchtop device. This was a device that just sat on the bench. That doesn't look anything like a modern CPU. But people had the vision and the creativity and the imagination to realize that, hey, this was really special. So in 1958, Jack Kilby at Texas Instruments, he made the very first integrated circuit. And this is not much to look at, but this basically had a PN junction and passive components, and it was basically a simple RC oscillator. And it looks crude, but this was before the era of really well-controlled clean rooms and techniques. Nevertheless, it was basically ushering in the next revolution to where we are today. And this is a CPU from Intel. It has 1 billion transistors. You can buy it for probably $200. And it's just like amazing progress that unless you really kind of open up your mind, it's really hard to connect the dots in 1947. So that's kind of where we are now, is I think we have a really open mind about how to do computation. So to draw an analogy, a parallel to the first transistor would be the first OPO that was demonstrated also at Bell Labs. It turns out they were doing pretty good work because they made the first transistor and now the first OPO. So this was the first building block. And again, it doesn't look like much. It was on a benchtop with a large crystal, and it was a little bit finicky. But things changed. There's been a few OPOs since, but the first integrated OPO was developed at Stanford about 2 years ago. And now everything's different. You take basically something that had to sit on a benchtop, and now it's shrunk down into these nanometer and micron scale devices. So a really exciting time. So we're now thinking, okay, what could happen next? And now we're trying to take these device breakthroughs and make large systems that are kind of parallel to the central processing unit. Although I think a better way to think about it is actually a photonic accelerator on a chip. Because these chips, although they might not replace a CPU, I do think they will have tremendous benefit as an accelerator, just like a GPU that you plug into some heterogeneous compute architecture. So these photonic circuits, we're envisioning thousands or more of elements, and really devices that can be more efficient than silicon electronic computing. And I think they're going to excel at tasks in machine learning and linear algebra and optimization problems. Actually, those are some of the world's biggest problems and kind of the biggest of the big data tasks. So this is what we expect. So I'll point out the work that we're doing at NTT Research, and we're looking at new ways of computing, not based on the traditional quantum computing model, but based on doing computation with what's called open dissipative quantum systems. And this is a kind of a paradigm shift. So I think everything I talked about on my first slide, that was all done using conservative Hamiltonian dynamics that basically require very, very low loss to function, or else you get qubit decoherence. What we're actually pursuing are architectures that are robust to noise and even use noise to help with the computation. So it's actually a totally different shift, and we're really excited about it. And all of the nonlinear optics I've talked about today directly support those projects. But we also have a couple other projects at NTT Research with collaborators. So Ryan Hammerly and collaborators at MIT, Ryan also works at NTT Research. And we have some edge computing architectures that would really benefit from some of the breakthroughs I've talked about today. Likewise, there's physical neural networks and machine learning with photonics that would also basically, it would be a different world if this can be applied to machine learning. And we have collaborators at Cornell University who are also NTT Research scientists that are working on those problems. But there's also a lot more that I didn't have time to talk about today. It can be used for spectroscopy and greenhouse gas sensing. You could actually fly some of these chips on drones and check out the atmosphere, or gas pipelines. You can do bioimaging, quantum enhanced sensing. There's a lot here. But I think really the highest impact thing right now is computation. So what's next? So we've demonstrated the basic devices. What's next is really to scale this up to make it compete with silicon photonics, or I guess compete's the wrong word, but at least kind of appear to silicon photonics so that this functionality can be realized in a reproducible way, and then we can change the world. So thank you for your time.